Perfect. Thank you very much. I just checked that everybody can see slides and things. And like I said, if everybody wants to ask questions, please go ahead and jump in, but we can also wait until after the recording. I'll say thank you for the organisers for inviting me. It's a nice opportunity to talk to new people and hopefully share some ideas. So yeah, today I'm going to be talking about generalising Kapranov's theorem for hyperfields, and I'm going to introduce all of these things and something called a RAC map. So first of all, I'd like to just say that say thank you to all of these kind of institutions for funding and letting this kind of opportunity happen. This was partially done during my PhD at Swansea University in Wales in the UK, and some of the work has been ongoing and will be finished in my postdoc at Bristol University, which is a Heilbronn Fellow. So thank you to all of those institutions to let me do this. So the structure of today's talk will be introduction, refresher, recap of some tropical geometry and some ideas about Kapranov's theorem. If you haven't heard of it before, that's okay. I'm going to run through that. Then I'm going to introduce the objects that I like to work with called hyperfields, which allow addition to be a little bit funky and a little bit weird and have multiple outcomes. They're a bit strange to begin with, but hopefully you understand the appeal of them when we get through the talk. Then I'm going to talk about some of the first results that is in my first paper that is on the archive, and then the kind of more recent developments are with my collaborator Ben Smith from Manchester, where we're building on the original work to kind of develop it further, which is quite nice. So let's start with some tropical geometry. I'm unsure what people's background is, so I'm going to, if it's too simple, don't worry, we'll ramp it up towards the end. So in tropical geometry, we work over the tropical semi-ring, so R union negative infinity, max plus algebra, and negative infinity is the tropical additive neutral element, and 0 is the tropical multiplicative neutral element. And we can do lots of awesome things in the tropical semi-ring. And one of them is look at polynomials. So polynomials are just formal sums using the tropical arithmetic. They're piecewise linear objects when you evaluate using this kind of max plus setting here. And from polynomials, we can study the roots of the polynomials. So in tropical geometry, we look at roots in a slightly different way. There's many different definitions or ways to view roots, but the one I'm going to talk about today is points in a variety of where the maximum is achieved more than once. We have the isomorphic tropical semi-ring using infinity and min rather than minus infinity and plus, but this is what I'm going to stick to today because it maps to the hyperfield way of thinking quite nicely. So one of the ways to get to grips with this is to think about an example. So if you take a two-variable polynomial in x and y, so x tropical plus y tropical plus 0, when we evaluate this using the tropical operations, we just get the maximum of the three monomials, x, y, and 0. Then, like I said, a tropical variety, or the variety of this tropical polynomial, is described by the following set. So it's this classic picture in tropical geometry. If you've ever studied any tropical geometry before, you will have seen something like this. So it's the three kind of arms of the variety correspond to where two of the monomials are equal and achieve the maximum. So can you see my mouse? Are you able to see my mouse as well? Yeah, so this is where x is equal to 0 but is greater than y. This is where y is equal to 0 but greater than x, and then this diagonal is where x is equal to y is greater than 0. This should be strict because we have the vertex in the middle. The point is where all three monomials are achieving the maximum. There's some wonderful things we can do with tropical varieties. This is a tropical plane curve. There's lots of things that we can say and some nice combinatorics we can do with describing roots. But one of the things I'm going to talk about today is how we translate from normal algebraic geometry to some tropical geometry. So this is called, one way of describing this is an operation called tropicalization. So given objects over a field, then these can be viewed under a tropicalization map to the tropical setting. So this starts off with something called evaluation. And evaluation is a map from a valued field K. Normally it's algebraically closed, but spare those details for a minute, and this should be actually our union negative infinity. We want it to go to the tropical semi-ring. So it takes A to negative infinity if and only if A is 0. So it kind of takes the additive neutral element over the field to the additive neutral element over the tropical semi-ring. It turns multiplication over the field into addition over the tropicals, and it takes addition and turns it into this maximum operation. So this is one of the building blocks we use to translate things from algebraic geometry, classical geometry to the tropical setting. And what we can do is we can build on this and use this to look at polynomials instead of just elements of the field. So, okay, so there's 2 points here. I use, also noting that I use subscript star for the induced map of polynomials over the field to R, just to kind of differentiate between when I'm talking about tropicalizing points and tropicalizing polynomials. And capital trop will be for n tuples from Kn to Rn. So hopefully I've got it consistent throughout the talk. If there's any questions or non-consistencies, please jump in and quiz me on it. So taking a normal polynomial over the valued field, we can tropicalize this by adjusting all of the arithmetic from multiplication and times, and we transfer that to tropical arithmetic, so maximum and plus. And we also take the valuations of the coefficients here, the valuations of AI. So this is one way of taking a classic polynomial and turning it tropical, and we can also take points in n space and take them to a tropical n space by taking the coordinate-wise valuation. So what I'm trying to do here is I'm trying to build up all of the tools we need to explain what Kapranov's theorem means and tells us in the tropical setting. So what we can do is, the big picture here is we can kind of look at this square, this diagram, and understand how these different operations interact. So the one across the top is, again, seemingly have dropped the star, so imagine there is a subscript star here. This takes polynomials in 1 to n variables over the field and tropicalizes them, like we just said, adjusting the arithmetic to tropical arithmetic and taking a valuation of the coefficients. We can look at varieties in the classical algebraic geometric sense by looking at root solutions of our polynomials, but we can also, like we've done, look at roots of the tropical polynomials, so tropical roots of our tropical polynomials, where points where the maximum is achieved more than once. And then down the bottom, we can also tropicalize points in n space. So one of the questions that's talked about in tropical geometry and has been proven is Kapranov's theorem, which looks at when and how these interact, and the relationship is very nice. So the theorem is stated here, but I'll kind of flesh it out and talk around it. So, like I said, given an algebraically closed field K with surjective valuation and this trop map from this valued field to the tropical semi-ring, then for some Laurent polynomial, you can kind of go around either side of the square and the diagram we had in the last slide, and you end up with the same set. Sometimes you might need to take the closure, but I'm admitting some precise details just to give you the general picture here. So you can take the tropicalization of a polynomial and then look at the tropical variety of this as a set, or you can take the variety of our polynomial classically, the solutions, when it's equal to 0, and then tropicalize these points. Again, I feel like I've already made 2 errors in my slides, but this should be capital T for endpoints. Apologies for that. But what we can do is we can go either way, and you end up with the points correspond here. So the question that I was working on in my PhD was taking some of these results, including Kapranov's theorem. How far can we stretch them? How can we loosen some of the constraints? Do they just hold in this setting, or is there a more general setting where these relationships hold? So yeah, can we understand this type of question when trop is replaced with some general class of maps? So instead of some valuation from some valued field to the tropical semi-ring, let's loosen some of the constraints and give a slightly more general type of map. Do these results still hold? So this was and what I'm going to do today is hopefully give you some examples and show you that it does in some nice, more general settings. So on to part 2. this is where I'm going to introduce objects called hyperfields. And if you haven't seen them before, they are a little bit wacky to begin with, but that's okay. It's all part of the charm of working with something new. So to give some motivation and introduction, there's kind of a rhetorical question here, like what possible answers can you get if you had a positive and a negative real number? So all that you know is one is positive and one is negative, and you don't necessarily know the size. They do have some size, but you don't necessarily know the size. So these are kind of poorly coded diagrams here, kind of giving you the three situations that can happen. So you can either have that the positive one is bigger, negative one is bigger, or that they have the same size and they will cancel. So what I'm trying to show here is that hyperfields capture information when maybe you don't know all of the information. So this is captured by something called the hyperfield of signs, which has as its set of elements -1, 0, and 1. And instead of me giving you the precise definition of a hyperfield, I'm just going to show you that the hyper addition, or the addition on the hyperfield here, is multi-valued. So this 1 plus box plus is going to be our hyper addition, plus -1 could be all three of these outcomes. So what this is trying to capture is saying that given some positive element plus some negative element, what possible outcomes could you have? So this is a set. And kind of to make this slightly more formal, a hyperstructure we're going to denote with blackboard H or blackboard capital letters, allows the addition from H cross H to the non-empty power set of H. So there is other kind of generalizations of fields, talking about partial fields and tracks and things like this, but the addition here is always going to be defined. There is hypergroups and hyperrings and hyperfields that kind of generalize and mirror some of the axioms of groups, rings, and fields. So this is the example I wanted to kind of introduce to begin with, because it's nice and visual, but hyperfields have been used recently to explore generalizations of some tropical geometry, and they were used very recently as well to encapsulate some matroid theory as well, because matroids over the sign hyperfield here are this equivalent to oriented matroids, and we'll come on to some ideas a little bit about that as well. We can talk after as well. So I'm going to give you some more examples now, rather than bog down with precise definitions, because I don't think that's necessarily productive. So this is the tropical hyperfield. This is one of the main reasons there's this connection between tropical geometry and hyperfield theory. So we have that the ground set is the same, R union negative infinity, and that we have our tropical multiplication over the hyperfield is the standard addition of the real numbers. But we have this quirky definition of hyperaddition. So again, we take the maximum of two elements if they're not equal, but if they are equal, then we take that element all the way down to negative infinity, the whole kind of open interval, but closed because it includes negative infinity here. So this is why it's multi-valued. You get this interestingness when you have the two elements equal, and this is kind of mirroring, trying to capture the kind of idempotentness of the tropical semi-ring in the classical setting. Another example here is something called the phase hyperfield. So this is the unit circle, union 0. The multiplication is inherited from complex numbers. And what these two statements down here are saying is, if you have 2 points on the unit circle in the complex plane, and they're opposite, they're antipodal points, they're kind of additive inverses of each other, you get those 2 points and 0. But if they're not opposite each other, they're kind of slightly closer together, you get the open arc between them. And there's variations of the phase hyperfield where you actually get the closed arc between them rather than the open arc, which I will come on to later. So this is a one hyperfield, and a couple more that I'll introduce just so you get a nice flavor of the landscape here. Is one of the smallest hyperfield is the Krasner hyperfield, where it's just the hyperfield of two elements, and 1 plus 1 is equal to 0 and 1. This, if you're thinking about the category of hyperfields, is the terminal object in the category. Because everything, you can take every hyperfield to the Krasner hyperfield by just sending everything non-zero to 1 and everything, 0 to 0. But we'll kind of move on. So another key player in the rest of the talk, along with the tropical hyperfield, is this tropical complex hyperfield. And don't worry if this looks like a big definition, because I've got some pictures on the next slide which hopefully make it slightly more intuitive. So again, the ground set, the underlying set is the complex numbers, and the multiplication is inherited as standard multiplication. But the addition is, again, takes a little bit of explaining. So it's essentially looking at how the absolute value of the element. So if x is further away from the origin, has a bigger absolute value, then you take that. If y, you take this. If they have the same absolute value, but they're not additive inverses of each other in the classical setting, you take the shortest closed arc between them on that radius. And then if they are actually antipodal, opposite points, additive inverses in the normal complex setting, then you get the disk of that radius, the closed disk. So to make this slightly more visual, I feel like seeing pictures is always a nice way to make things more secure. Is here are three examples. So on the left, if you the point is that we're adding these 2 points. So these 2 points are points of our tropical complex hyperfield, and we'd like to add them together using the hyperaddition. So on the left here, this one has a bigger absolute value. So this is the outcome of the hypersum. The two here are meant to, I hope that they are on the same radius. So you end up with the closed arc, including the 2 points themselves. Again, the shortest closed arc, so it wouldn't go this way around. It's the shortest between the 2 points. And then if they're exactly opposite each other, on the same radius, then you get the whole disk, the closed disk including points. So these are all kind of new ideas, different ways of doing additions. Hopefully those have all kind of made sense. I know it's a lot to take on, especially all these new ideas, but hopefully some pictures have made it a little bit more concrete along that lines. If there's any questions, please jump in. I know it's a lot of new ideas to begin with, but looking at the results.
I want to ask about previous slide. So we have some dependence on the basis or height. Previous slide,
sorry, yeah. This one?
Yes, because in case we rotate this
there is
crossing, we can do something seems.
Yeah, you kind of fix the ground set as the standard complex numbers, and you fix the standard basis there. Yeah, I would say. Does that aid your question, or?
Yes. And you stated it is tropical complex.
Yeah, it's coined in the literature as the tropical complex, because in the tropical hyperfield or the tropical semi-ring, you end up taking, when you take a sum of elements, it's the maximum elements that are contributing to the outcome of the sum. Here it's almost the same, but you're not taking maximal elements, you're taking elements of maximal absolute value, I suppose.
It's just notation. There is no analogy with simplicial complexes or polyhedral. Just notation, yes.
Sorry, yeah, tropical. Yeah, I would call it the tropical complex hyperfield, just to say that we're working over kind of the complex numbers rather than yeah, perfect. Is that okay?
Yes, thank you.
Perfect. Okay, great. So now we've looked at some hyperfields and understood some of the structure and got some examples to work with. How do we get between these hyperfields? I said at the beginning or the end of the last section, we're going to replace tropicalization or our valuation with a more general class of maps. And this is the class of maps we're going to look at for today's talk. So we're going to look at something called hyperfield homomorphisms. So as you'll notice here, I put the kind of key thing up between these two things. So if you're given H1 and H2 are two hyperfields, then the structure is slightly looser because we have inclusion here rather than equality, because this addition in the bracket here could be a set rather than a singleton, and then this addition over here of the outcome could also be a set. So we have that there is inclusion rather than equality. So this again is loosening some of the constraints on what maps we want to look at. And yeah, some other kind of details is that 0 is 0. Well, the additive neutral element is sent to the additive neutral element, the multiplicative neutral element sent to the multiplicative neutral element, and it multiplication behaves as expected. So some examples that we're going to look at today is, like I said, you can take any hyperfield to the Krasner hyperfield by sending 0 to 0 and everything that's not 0 to 1. The sign map, the sign hyperfield homomorphism takes the real numbers to the sign hyperfield by just taking the sign of the real number. One of the maps we're going to look at in detail today is this map from TC, the tropical complex hyperfield, to the tropical hyperfield, which takes eta of z is take the absolute value and then take the logarithm of z. So you might be able to see that we kind of look at maximums of absolute values over here, and we look at maximums here. So this map does kind of make sense when we're talking about the compatibility with inclusion with regards to the addition over the hyperfield. And a final one which I'll introduce as well is this phase map, which goes from the complex numbers to the phase hyperfield. So it just looks at how far around the circle we are. So these all of these maps can be actually viewed as quotient maps, but I won't kind of go into too much detail about that. It's kind of reducing some structure and remembering some other structure. So the last kind of couple of tools that we need to build up is the same as what we did over the tropical semi-ring. How do we observe and work with polynomials, and how can we look at roots? Because the plan is, as we're making this ascent to some of the results that I've got, is we need to build up these tools to kind of look at this diagram of when can we take between hyperfields and then look at roots on either side, and how compatible are they? So again, just to build up our toolbox, we have polynomials are just formal sums over n variables using the hyperaddition and the multiplication over the hyperfield. Again, I'm using f subscript star here for this push forward instead of trot. We're kind of mirroring this idea of using the push forward, which takes f of the coefficients and will alter the structures on alter the operations. Sorry, excuse me. So it's not depicted here, but this would be the hypersum over H2. The key difference as well over hyperfields, we're trying to generalize this idea of a root. So an element is the root if and only if, when you take your polynomial and evaluate your polynomial at this element, the sum, the hypersum, this output could be a set. So instead of saying this is equal to 0, like a classical root would be, we say that this contains 0. So that the set that is produced by the outcome of evaluating P at this element contains the additive neutral element. And again, for formality, the variety of P is all these elements where 0 is in P of A. So an example of these ideas is if you were to take the polynomial P of x is equal to x squared minus 7x plus 6 over the real numbers, then, like we said, the induced map of polynomials, sine star of P, just remembers the signs of the coefficients and also turns the arithmetic into our arithmetic over the hyperfield of signs. So it results in just x squared plus minus x plus 1. And then we can say that the element 1 is actually in the variety of this thing, because when you would evaluate, you'd have 1 squared, which is 1, plus minus 1, plus 1, which includes 0. Because 1 plus minus 1 is the whole set, and then you add 1 to this, you're still remaining with the whole set. Perfect. Okay, so these are the new ideas that we need to get to grips with hyperfields, and hopefully now I'm going to show you how we can link these. Perfect. Okay. So two key facts for the onward journey is that roots over the tropical hyperfield are very similar to roots over the tropical semi-ring. So it's when you evaluate your polynomial at A and at least 2 of the monomials are contributing to the maximum.
Sorry, I just touched the mouse pad and I think I drew on you. Sorry.
No worries, that's okay. Yeah, that's not a problem.
I didn't know that this was actually visible. Okay, sorry.
Yeah, no worries, that's okay. No problem. So yeah, sorry. The roots over the tropical hyperfield are very similar to the roots over the tropical semi-ring. It's where you evaluate your polynomial A, and at least two of the monomials are contributing to the maximum. So there's not one monomial that's the maximum here. So roots over the tropical complex numbers, tropical complex hyperfield are very similar. So it's an element B that when you evaluate your polynomial Q at B, it has at least two monomials contributing to the maximum, and the hypersum of these monomials has to include 0. So we have over the tropical hyperfield that it will include 0 because it's idempotent in that sense, but also over the tropical complex we have this extra condition. So to make this slightly more intuitive, kind of if you plot these monomials that achieve the max, that are contributing to the maximum in the complex numbers, and then you would look at the convex hull of this, it kind of would include 0. So they have to be distributed around the circle of that maximum radius enough to have 0 in it. So I've introduced all of the tools. I've given you some motivation of the result we're going to look at. So now I'm going to move on to some of the results. But if anyone has any questions, or we want to take 5 minutes or comments or anything, I'm happy to pause here because we're about halfway through on my slides and roughly on time as well.
I think you just can go on.
Yeah, perfect. No worries. Like I said, if anyone's got any questions or comments or wants me to go back, please just jump in. But yeah, so now given, hopefully we've done enough groundwork, hiking up using all of our tools to understand the landscape, we're going to make an ascent to some of the results that we've managed to prove. So these are still building blocks, but they're crucial to the later results. So for any hyperfield homomorphism from H1 to H2, we have this one-way inclusion already. It's defined it's just as a consequence of some of the axioms of hyperfield homomorphism. So we have that if you take the variety of a polynomial over H1 and then push these n tuples forward, this will be a subset of if you were to push the polynomial forward and then look at the roots over H2. So this happens for all hyperfield homomorphisms. It's not unique to any special ones, but because of the way the inclusion holds in the definition, we will have this inclusion always holding. So what we want to look at is the reverse inclusion of this. So when I was doing my PhD, we looked at the way that Kapranov's theorem holds over the tropical semi-ring and tried to understand what the key aspects of this was. And we realized that we wanted this inclusion the reverse way around, is what I have here, but you only actually need it for univariate polynomials. And then you can use this to prove it for polynomials in n variables. So what we did is we introduced this notion of something called a RAC map, and this stands for Relatively Algebraically Closed. So a map between H1 and H2 is RAC if for all polynomials over H1 in one variable, when you push these forward, the varieties of this push forward is a subset of the push forward of the variety of the original polynomial. So it's the reverse inclusion here, but all we're requiring is that it happens for univariate polynomials, not variables in n, not polynomials in n variables, sorry. And what we tried to do is use this property. Well, we tried to explore if any hyperfield homomorphisms had this property, and then try to use it to prove a full generalized Kapranov's theorem. So immediately I can give you two examples where this property does not hold. So if you take the sign map from the real numbers to the sign hyperfield and take a very similar polynomial to what we had before, so x squared minus x plus 1, then again, the sign map just remembers the signs of the coefficients and exchanges our normal arithmetic for our hyperfield arithmetic. The polynomial p has an empty variety over the real numbers, but the polynomial under the induced sign map of polynomials actually has a root. So here there is an element of the variety of sin star of p but there is nothing in the variety of P to push forward to this. So there's an example of not RAC because the inclusion one doesn't even hold. Another example of this is taking the map from the complex numbers to the phase, because when we were initially looking at this, we thought the real numbers aren't algebraically closed, so maybe there's something that might help by looking at an algebraically closed field to a hyperfield. And again, taking a similar polynomial, so x squared plus x plus 1 over the complex numbers, then it's actually shown in work by Matt Baker and Oliver Lorsteid that the push forward of this polynomial has a root for each a is equal to ei theta, where theta varies between this interval here. So it actually has kind of infinitely many roots in this interval. And the point is that each of these roots can't be lifted back to a root of the original polynomial because there is only 2 of those. So there is elements in the hyperfield that are occurring as roots that are not images of roots of the original polynomial. And this kind of shows some pathological behavior that over hyperfields, way more roots can crop up. There's a whole interval of roots for a degree 2 polynomial here. So what we tried to do with this RAC property is contain this behavior of roots. So there is actually an example of a RAC map. We were worried for a while that there wasn't going to be, but this is the nice building block. So the map I talked about earlier, this eta from tropical complex to the tropical semi-ring is actually a RAC map.
Okay, while you're out at all of this, what about something like Nullstellensatz? Does it also work, or?
It does. That's something that's also been worked on, but we were focusing on the difficulty is thinking about when you're thinking about ideals over the hyperfield, there's not a nice notion of this, so you'd have to look at a map between a field and a hyperfield. And I wasn't going to mention that actually, but it is a good question. There has been some kind of ideas working towards that. But I suppose I'll foreshadow it a little bit. If you were to look at a purely a map between a hyperfield and between 2 hyperfields, defining an ideal over this polynomial setting is quite difficult because when you multiply 2 polynomials over a hyperfield, the outcome could be a set of polynomials rather than one polynomial. So the set of polynomials over a hyperfield isn't a hyperring; it's something more general. So, but yeah, that is an aim as well to understand that. So, like I mentioned earlier, the way that roots are achieved over the tropical hyperfield and the tropical complex hyperfield are very interlinked. So it's about when monomial terms are achieving their maximum more than once, and with this kind of negative convex restraint over the tropical complex hyperfield. And it's the fact that this eta map has some nice order preserving properties. So this is actually a RAC map. It's a really nice example. And what we did is, can we now build on this RAC property of univariate polynomials to generalize it to n-variable polynomials? Okay, yeah, so a nice corollary of this is that the tropical complex hyperfield TC is algebraically closed. So in this sense, there's been some nice work to understand that the tropical semi-ring is algebraically closed, and in a similar sense, the tropical hyperfield is algebraically closed, that every univariate polynomial has a root that actually has exactly the number of roots counting multiplicity as the degree of the polynomial. This is not quite the case of TC, but this lifting property using RAC is kind of analogous to saying that TC is algebraically closed in a sense that every univariate polynomial has at least one root. So this was the main result of the first chunk of work that happened during my PhD. So this is the generalized Kapranov's theorem. And this says, given a polynomial in n variables, then if your map from some general hyperfield H to the tropical hyperfield is RAC, so there's this lifting property in one variable, then actually you can have the lifting property in n variables. So the variety of the push forward of the polynomial is equal to the push forward of the variety of the original polynomial. So this was really nice. It was a nice kind of breakthrough to say that we can actually say Kapranov's theorem in this more general setting where we loosen the restraints on the maps rather than just using valuations and tropicalization. And this was nice, but there's always room for improvement and more generalization. So we said, can T be replaced here with other hyperfields? So instead of relying on going to the tropical hyperfield like a tropical semi-ring, can we say something more general? So are there more classes of RAC maps? I think on the next couple of slides, I give a little bit of intuition behind some of the proofs. So this is a very similar structure to the Kapranov theorem. So we're looking at kind of n variable polynomials here, and we had this inclusion this way around. So taking the push forward of the variety of the polynomial includes in the variety of the push forward of the polynomial in a nice setting for any hyperfield homomorphisms. And the reverse way, kind of without giving too much details, is saying that we can take an element over here that's a tropical root of an n variable polynomial. There's a restriction that we can make with certain nice choices to restrict the polynomial and the root to a univariate polynomial, and the restriction of the root is still a root of this univariate polynomial. We use the RAC property to pick our way across back to the hyperfield H in one variable, and then because our choice of restriction of polynomial and roots were, I say nice because I don't want to give all of the details, but precise enough that we can actually push this forward to an n variable polynomial and a root that the root pushes forward in a nice way as well. So instead of kind of going across back this way, we have to take our way round the structures and the building blocks that we've used to get there, using the RAC property here, like it is in the classical setting. So this kind of came to the project towards the end of my PhD, and then I met with Ben Smith from Manchester, who works in tropical geometry as well, and we started discussing some ideas, and there were some other recent developments in the area that related to this work, and we're actually currently working on another project to answer that question or 2 slides ago. Is there any more RAC maps? Can we go even further and replace T with more general hyperfields? And for the last portion of the talk, I'm going to talk about some results which aren't on the archive yet, but hopefully they will be in the next couple of months, because we're in the process of developing it. So some of the questions we were discussing before we started the project is to understand whether there are more RAC maps out there. Can we give some characterization? Can we give some classes of these maps, some nice constructions, and can we give some more characterization of the behavior of roots? And in turn, give a broader statement of Kapranov's theorem in general, rather than just H to T. Can we give two hyperfields in general? This looks like quite a busy slide, but it's just to give you some background theory. So Trevor Gunn is one of Matt Baker's PhD students at Georgia Tech, and he's done some really interesting work on these ideas of something called a tropical extension. So it's a way of creating a new hyperfield from a given hyperfield. So if you're given a hyperfield H and some gamma, some ordered abelian group, this is the split, or the tropical extension of H by gamma is you kind of adjoin gamma lots of H and with some extra additive neutral element. And I can go through the way the addition is defined, but I just wanted to present it here. The precise details of this aren't important, but the structure of understanding these, you can take a hyperfield and build another one by adjoining this kind of ordered abelian group this many times, can give you a new hyperfield. I can talk about these more in detail later, but I just wanted to. So there's been some work about this. And what we wanted to do is classify the hyperfields that are these tropical extensions. So a hyperfield is called stringent if the hypersum is greater than 1 to the size. It is a set only when 0 is in the sum. So something like the signed hyperfield, the Krasner hyperfield, the tropical hyperfield are all stringent, because the only time you get a set is when they're additive inverses of each other. You get 0 in there as well. But the phase hyperfield and the tropical complex are not stringent, because over both of these you can get an open or closed arc of a certain radius. This is a set, but doesn't include a 0 element. So stringent hyperfields are, without being biased, are way nicer to work with. There's a lot of properties that you can pull in and draw on, and they are significantly easier to study in lots of circumstances. So there's actually a classification of stringent hyperfields, what they look like, a decomposition. So if H is a stringent hyperfield, then it's isomorphic to one of these three tropical extensions. And the reason I've given two references here is because Bowler and Su gave a really nice description of this, and then it was rephrased and incorporated into Trevor Gunn's work in this new notation. So it wasn't quite given in this quite notation. They used semi-direct product notation, but that's why I've given both here, because they're both important. So if H is stringent, it's either isomorphic to a tropical extension of the Krasner hyperfield, a tropical extension of the sine hyperfield, or a tropical extension of a field in the classical sense. So this was a really nice classification. It gives a really nice grip on stringent hyperfields. We can say, if we want to prove something, we can split it into these cases and use properties of Krasner, sine, and fields, along with this ordered abelian group structure to really pick apart for stringent hyperfields. So again, an example here, the tropical hyperfield is isomorphic to K adjoin R, where R is viewed as an abelian group. And the tropical complex hyperfield is isomorphic to the phase hyperfield joined R. I've put a bar on here because technically, to be precise, you'd need closed arcs when you're taking the addition over the phase hyperfield rather than open arcs, but this is dependent on what part of the literature you're looking at. So during the first part of my work, I proved this theorem about Kapranov over hyperfields, but then I also wanted to start classifying this, and this was one of the results here. It was a small inclination into how we can classify these things. So a map from H1 to H2 it's meant to say a RAC hyperfield homomorphism here. If H1 satisfies something called the inheritance property and the multiplicity bound, and H2 satisfies the multiplicity bound. So what do these mean? The multiplicity bound says that given a polynomial of degree n, then the number of roots counting multiplicities is no bigger than n. So this happens over fields. Like if you have a degree 2 polynomial of the real numbers, you can at most get 2 roots, or they could be a double root. And the inheritance property is something to do with factorizations of polynomials over hyperfields. But the important thing was that this is how far I got in the first project. And when Trevor released his paper, he actually, a consequence of his work was that all stringent hyperfields satisfy the multiplicity bound. So they gave this classification, and the work that he did, if you're given a stringent hyperfield, it satisfies this multiplicity bound. This could be seen in Matt Baker and Oliver Lordsteid's paper as well, where they talk about Descartes' rule of sign and the Newton polytope rule, because they classify multiplicities for the sine, the Krasner, and the tropical as well. So combining these two things, what do we get? If you've got a field K, a homomorphism between a field K to H, and K is an algebraically closed field, which actually captures the inheritance property in the multiplicity bound, and H is a stringent hyperfield, then F is a relatively closed hyperfield homomorphism. So building on these two, we already have another class of maps. But we can actually go a little bit further as well. So can we talk about this in general? Not going from a field to a hyperfield, can we genuinely take a hyperfield, sorry, and go to another hyperfield without relying too much on the field structure? And what we need to do is, what we had to do was understand roots over these tropical extensions. And again, the details aren't incredibly important, but we came up with this lemma that talks about how when things are roots over tropical extensions. And it's very similar to when things are roots over the tropical hyperfield. It's about where there's some set J from 0 to n, such that the kind of GJs are greater than every other GI, and the 0 is in the sum of these coefficients here. So the elements are these CI GIs, and this was just the characterization we have. Again, I won't go into detail too much, because the point is that we were able to classify or understand how roots, or when roots occur over these tropical extensions, in a similar way to how they're understood over the tropical hyperfield. Using this result, we're able to come up with this nice class of relatively algebraically closed homomorphisms. So if you're given a RAC map from H1 to H2, then for some linearly ordered group, we can lift this to some induced morphism of these tropical extensions using the same ordered group gamma, then that is also relatively algebraically closed. So given one RAC map, we can actually induce this homomorphism and build another one. And what does this mean? So if you're given some algebraically closed hyperfield H, so every univariate polynomial has a root, then this is automatically RAC to the Krasner hyperfield. So we can lift this using some gamma, some linear group, to another RAC map. And an example of this is actually the example that we had that was RAC, this TC to T, is actually an example of lifting some algebraically closed map from the closed phase to the Krasner, adjoining this tropical extension by using the real numbers and lifting. So there's actually more structure going on there. So the example that was in the first part of the work is actually one of a larger class of maps which exists. So we were able to kind of uncover the details and understand what was really going on underneath the hood. And then what we did as well is, or what we are doing, is taking a RAC map from H1 to H2 in general, not from H to T, and proving a slightly more general Kapranov's theorem state that if you take the variety of the push forward of the polynomial, then this is the push forward of the variety. So we're not requiring to have something necessarily tropical or tropical hyperfield. We can do this for a general RAC map. And actually the proof mirrors a similar case with a few small tweaks and adjustments from the case to the tropical hyperfield. So to conclude, some of the questions that still remain, which is ongoing in the project with Ben at Manchester, is, does this fully classify all of the RAC maps? So given some RAC map from hyperfields and then using these tropical extensions, is that all of them? Are there other ones that can occur, or are they not? So we'd like to understand whether this fully classifies all of the RAC maps. If it does, it would be very nice. Or if it doesn't, can we find other classes of them? And can these results be used to form a statement of a fundamental theorem for RAC hyperfield homomorphisms? So in the classical theory, Kapranov's theorem is used to prove an idea of a fundamental theorem using ideals. Like I mentioned earlier, it's a bit tricky to understand the notion of a polynomial ideal over hyperfields. But there is still hope on these two questions that we're looking at. So thank you for listening, your questions, and for paying attention. Please, questions are welcome. I think we've got a little bit of time, and I also have a couple of slides of references if people are interested. But awesome, thank you very much.
Okay, James, thank you very much for your great talk. Let's thank the speaker. Are there any questions from the audience?
I have a random basic question, maybe related to definitions. So is that, so apart from like I guess working with hyperfields, an analog of like just roots of polynomials, can you say anything about multiplicities, or is it just like not really feasible since it's hard to talk about ideals?
So when you're talking about ideals in the classical setting over a field, you have it there closed under addition and multiplication. But the problem is that when you take two polynomials over a hyperfield, when you multiply them together, normally you'd like add the coefficients of terms that have the same kind of like power in the univariate case. This could result in a hypersum. So the output could be multiple elements. So it could actually, when you multiply two polynomials together, you could end up with a set of polynomials. So this means that you have multi-valued addition and multi-valued multiplication, which I think in the literature is something called a multi-ring rather than a hyperring. So you have two operations that are multi-valued. I'm not sure there's been, or a super ring maybe. There's been some work regarding that, which I'm not 100% familiar with, but there's also on the flip side another way of possibly viewing it. So there's been some work over the last few years regarding something called a tropical ideal, which looks at polynomial ideals over the tropical semi-ring, but with this underlying matroidal structure. So there's some kind of elimination axiom to do with viewing elements of the ideal as kind of vectors of a matroid, and you have this elimination axiom. So if you can eliminate some monomial, then the other element, there must be some element with that eliminated and some other relations on the monomials. So there's a paper by Matt Baker and Nathan Bowler that look at matroids over hyperfields. So one step could be to say, instead of defining an ideal in the standard sense, closed under multiplication and addition, can we say there's some underlying matroid structure like tropical ideals? But that's something I'd really like to work on, but haven't kind of reached out onto yet. I was trying to, even understanding just single polynomial kind of equations was a little bit tricky and took its time. So hopefully that gives you a bit of flavor.
What about some other standard operations like localization or so? How do I see that over a hyperfield? Is it defined? Does it make sense?
There's a lot of things over hyperfields which kind of need to be studied and kind of even from the categorical sort of way of viewing things. So I'm not sure if localization has been understood yet properly. I'm not sure. Sorry.
But what about tensor product?
What I do know is that so hyperfields are one generalization of fields. There's lots of kind of categories that pull away parts of the structure and say, oh, let's forget that we need this and how can we go general? And there's recent work, again, kind of involving Oliver Leuchtstein and Matt Baker and in their research group. So another generation is something called a pasture, and then a tract, and then a blueprint. And it's been shown that hyperfields don't have some structures, like they don't necessarily have co-limits in the category. So they kind of generalize a little bit further. And I think if to have as much structure or as much things working as possible, I think maybe ordered blueprints would be the way to go. But I don't think everything is defined for hyperfields. That's all I think all I can say there.
Are there any more questions?
Thanks. Oh, I just wanted to check if I missed something. So I guess what I was sort of originally asking about is that you mentioned things about just like roots of univariate polynomials. So maybe is it like sensible to try and say anything about like multiplicities, or is it just not feasible?
Yeah, great. So some of the motivating work for this was this Baker and Leuchtstein paper, and they introduced the notion of multiplicities for univariate roots of hyperfields, and specifically do it for the Krasner, the sine, and the tropical hyperfield. And what they do is they try to understand the factorization process, that if you have a root, you should be able to in sense factor out x minus this root. But like I said, multiplication of polynomials is tricky. So they have to use this recursive formula that says when you have the multiplication of two polynomials could be a set. So your polynomial should belong to this set, but then this polynomial could belong to lots of different factorizations. Like essentially factorization isn't unique over hyperfields. So it becomes a little bit trickier, and you have to say the multiplicity is the maximum number of times you can take out this linear factor with our polynomial still belonging to it. And over the hyperfield of sines, this kind of corresponds to the number of sign changes in the coefficients, and then the number of sign changes if you replace x with minus x. So like Descartes' rule of signs in that sense. And then over the tropical numbers, it's the horizontal length of the Newton polytope, I think, of the valuations of the coefficients. So there is some really interesting things there, and the work that I mentioned by Trevor Gunn discusses multiplicities in more details, which has allowed him to say that stringent hyperfields satisfy this multiplicity bound by saying that when you have a stringent hyperfield, you don't have too many roots in it, in my sense. So yeah, but it's quite tricky because when you factorize, it's not unique. No, I still factorizing polynomials over hyperfields is, lots of ways of doing it.
All right, thanks.
Okay, if there are no more questions, I will stop the recording.
Perfect, I'll stop.